there is a volcano that most people have never heard of.
It sits nearly a mile beneath the surface of the Pacific Ocean, 300 miles off the coast of Oregon. It has no name that appears on road signs, no evacuation zone with a radius measured in city blocks, no ash plume visible from shore. It does not look like a volcano. It does not behave like the volcanoes that make the news. It is not dramatic in any of the ways that attract cameras or press conferences. And yet, as of tonight, it is among the most carefully watched geological systems on the planet. 140 instruments are running on it right now. 660 miles of fiber-optic cable connect those instruments to the surface in real time. A physics-based forecasting model developed by researchers in Sweden and Switzerland is processing its data continuously,
looking for the signal that will precede what scientists at Oregon State University have been describing, in their own words, as inevitable.
The question they are trying to answer is not whether it will erupt. The eruption is expected. The question they are racing to answer is when.
And the answer, based on everything the instruments are showing tonight, is now, not tomorrow, not next year, now.
The mid to late 2026 window that Oregon State volcanologist Bill Chadwick has been documenting since December of last year is the window we are currently inside.
The seafloor beneath the caldera of the Axial Seamount is sitting at a higher inflation level than it was before the eruption in 2015. The magma is there. The pressure is building, the instruments are running, and the model is watching.
What those instruments cannot tell you, and what the model does not account for, is that human beings have been watching this sequence before. Not with fiber-optic cable.
Not with pressure recorders or bottom-mounted seismometers. With oral tradition. With carved record.
With navigational astronomy, and with accounts that were set into stone and into chant before any of us had a name for what a subduction ridge was. Tonight's report covers what the Oregon State University Regional Cabled Array is showing right now. It covers the history of the Axial Seamount's 3 documented eruptions in 1998, 2011, and 2015, and what that eruption history tells us about the timing and character of what is coming. It covers the pattern that connects each eruption to a documented threshold of inflation and seismicity, and it examines the new physics-based model that is, for the first time, running a prospective forecast in real time.
And then it goes somewhere the instruments cannot, because there is an older record.
There are traditions from communities that have lived beside, above, and inside the Pacific's volcanic floor for thousands of years
that described what happens when the ocean bed opens.
They used different words. They used different frames.
But the event they were describing, fire from below the water, the seafloor lifting,
the pulse of heat through cold ocean, is structurally the same sequence that Oregon State's data shows is approaching. That layer comes later. We will get there. Before that, for those of you who are new here, this channel files one report every night. We do not speculate ahead of the data. We follow the official agency readings. We trace the historical record, and then we go one layer deeper than the instruments can reach. If that is something you want to stay close to, subscribe before the report ends. And tell us in the comments, where are you watching from tonight? We have viewers who file from every coast in this network, and we always want to know what the map looks like. We build this each night from where you are watching. The full record starts now. There is a detail in tonight's data that no mainstream report has addressed in the last 30 days. The Axial Seamount seafloor is already inflated beyond the level at which it erupted in 2015. That means the geological trigger point that the 2015 eruption represented has already been passed. The system is not approaching the 2015 threshold. It has exceeded it. The reason it has not yet erupted is that Oregon State's updated model identifies a second, higher threshold approximately 20 centimeters beyond the 2015 eruption level that may need to be reached before the next eruption is triggered. That number will matter later in this report. Keep it in mind. The question of how close the current inflation level is to that second threshold is exactly what the instruments are measuring tonight, and it is what drives the mid to late 2026 forecast window that Chadwick and his colleague Scott Nooner at the University of North Carolina have been tracking across a series of public updates. We are going to walk through everything the data shows, everything the prior eruptions tell us about what to expect when it happens. And then we are going to examine what communities who live on the rim of the Pacific have been saying about this kind of event for much longer than our instruments have been in. The water. The briefing begins. The Axial Seamount is located on the Juan de Fuca Ridge, a divergent plate boundary running through the northeastern Pacific Ocean, roughly 300 miles west of the Oregon and Washington coastline. Its summit caldera sits approximately 1,400 meters below the ocean's surface, nearly a mile of cold, dark seawater overhead. It is the most active submarine volcano in the entire northeastern Pacific, with a documented eruption history stretching back across the last several decades and geological evidence of dozens of eruptions across the previous 8 centuries. The 3 eruptions that fall within the modern scientific record occurred in January 1998, April 2011, and April 2015. Each of those eruptions followed the same general pattern. The seafloor around the caldera inflated steadily in the years preceding the eruption as magma accumulated beneath the surface. Seismicity, the rate of small earthquakes beneath the caldera, increased in the final approach to the eruption.
And then, at a specific inflation threshold, the eruption occurred. Lava flows erupted from fissures on the caldera floor and along the volcano's flanks.
New sections of seafloor formed, and the ground surface of the caldera dropped sharply as the magma reservoir beneath it drained. Following each eruption, inflation began again as the magma supply replenished. This is the cycle the instruments have been watching since the 2015 eruption ended. The primary monitoring infrastructure is the Ocean Observatory's Initiative Regional Cabled Array, operated by the University of Washington and funded by the National Science Foundation. This system consists of more than 660 miles of fiber-optic cable laid across the Juan de Fuca tectonic plate, connecting more than 140 instruments directly to shore in real time. Those instruments include 4 cabled bottom pressure recorders, devices that measure seafloor uplift by tracking changes in water pressure at the caldera floor, and a network of seismometers that record the rate and distribution of earthquake activity beneath the seamount. The data these instruments generate is publicly available, continuously updated, and tracked in real time by researchers at Oregon State, the University of Washington, and collaborating institutions.
There is a number in tonight's data that no mainstream outlet has highlighted.
The current seafloor inflation at the Axial Seamount caldera is already higher than it was immediately before the 2015 eruption. That statement is precise and requires unpacking. The 2015 eruption occurred when the caldera floor had recovered to a specific inflation level above its post-2011 eruption baseline. OSU researchers identified this level as an eruption threshold based on the pattern from the 2 prior eruptions. Following the 2015 eruption, inflation began again and has been building since. The rate of that post-2015 inflation was initially rapid, then slowed significantly beginning around the summer of 2023, approaching nearly zero. It then picked up again in the fall of 2023. By early 2026, the total uplift since the 2015 eruption had already exceeded the uplift level recorded before the 2015 event.
This is why the system is described as being beyond its prior eruption threshold.
However, the same researchers have identified a second threshold, approximately 20 centimeters higher than the 2015 eruption level. This second threshold reflects the observation that each successive eruption at Axial has required a slightly greater amount of inflation before triggering the magma reservoir, appears to become slightly more resistant to rupture with each cycle. The current forecast window of mid to late 2026 is based on the rate of inflation required to reach this higher threshold.
The rate of seismicity has been lower than expected through early 2026.
Bill Chadwick, in the most recent public update based on data through the 26th of March 2026, noted that both the inflation rate and the earthquake rate have been lower since approximately January 2026.
He described the system as being in a lull. This does not mean the eruption is not approaching.
It means the approach has been slower than projected at the higher end of the forecast range. We will return to what a lull in seismicity has historically meant in the months before an axial eruption. Keep that pattern in mind. because the 2015 record makes it relevant. The Eruption Forecasting Experiment currently running at Axial Seamount is the first of its kind to operate prospectively rather than retrospectively. Previous eruption forecasting models were validated by running them backwards through data that had already been collected. The current model, developed by Tsinghua Lei of Uppsala University in Sweden and Didier Sornet of ETH Zurich in Switzerland, was designed specifically to function in real time. It is processing Axial's current data as it arrives, and its forecast will not be released publicly until after the eruption occurs. This design is intentional and significant. It removes the possibility of post hoc adjustment, the tendency to reinterpret the model's performance in light of knowing when the event actually happened. The eruption, when it comes, will test the model's prospective accuracy for the first time. That test is now inside its forecast window. The 2015 eruption serves as the closest available analog for what to expect. On the 24th of April 2015, the regional cabled array detected the beginning of the eruption in real time.
Seismicity beneath the caldera spiked to tens of thousands of earthquakes per day.
The caldera floor dropped by approximately 2.5 meters as the magma reservoir beneath it drained.
Lava erupted from a series of fissures running along the caldera and down the flanks of the volcano.
The eruption produced approximately 110 cubic meters of lava per second at its peak, covering an area of roughly 69 square kilometers of seafloor.
It lasted approximately 2 weeks before activity subsided. None of this was visible from shore. The ocean surface above showed no sign that a volcano was erupting a mile beneath it. No vessel was in immediate danger.
There was no tsunami, no ash plume, no atmospheric disturbance detectable at the surface. The only way scientists knew the eruption had occurred was because the instruments were running. Before 2015, they would not have known until researchers returned months later to find the new lava fields. Now they know in real time. The seismicity threshold that Oregon State's researchers have used as a secondary indicator of eruption imminence is 500 earthquakes per day. In the months before the 2015 eruption, daily earthquake counts beneath the caldera reached and exceeded this level. In early 2026, the daily count has been well below it, closer to 100 earthquakes per day on most days, with occasional bursts of several hundred.
This is what Chadwick described as the lull.
The question his forecasting work has not yet resolved is whether the low seismicity is a sign that the eruption is further away than the inflation level alone would suggest, or whether it represents a different kind of buildup, a quieter approach that nonetheless arrives at the same destination. The 2011 eruption is relevant here because that eruption also showed a relatively quiet seismic buildup before the event. The seismicity spike in 2011 was shorter and less sustained than in 2015. The eruption happened anyway. Whether 2026 will resemble 2011 or 2015 inches, its approach pattern is one of the questions the live forecasting model is trying to resolve. What the instruments do agree on is that the inflation is high, the magma is present, and the system is in the window. The second number in tonight's data, the gap between the current inflation level and the projected upper threshold, is narrowing. We will reach that detail before this report closes. Plant it here. The gap is narrowing. The University of Washington's seismometer network shows that the earthquake activity at Axial Seamount is distributed spatially in a characteristic pattern. Activity concentrates beneath the caldera floor and along a north-south trending zone called the North Rift Zone, and a south trending zone called the South Rift Zone. These are the primary pathways through which magma moves from the reservoir beneath the caldera, outward and upward toward the eruption vents. The 2015 eruption produced lava along both rift zones, with the South Rift Zone producing the largest volume. Monitoring the spatial distribution of seismicity across these zones, not just the total earthquake count, but where the earthquakes are occurring, and at what depth, is one of the primary ways researchers are tracking whether magma is beginning to move. There is a note in the current monitoring record worth filing. Since approximately March 2026, the spatial clustering of seismicity at Axial has shifted slightly. The earthquakes that are occurring are concentrated in a zone that sits along the upper portion of the magma reservoir interface, shallower than the typical background distribution. This is a pattern that, in the retrospective analysis of pre-2015 data, was associated with magma beginning to accumulate in the upper reservoir, rather than the deeper supply system. It is not a definitive signal, it is a pattern, and it is a pattern on the record tonight. The physical mechanism of an axial eruption is worth understanding in full, because it is not the mechanism most people picture when they hear the word volcano. There is no eruption column rising to the stratosphere. There is no ashfall blanketing agricultural land. The lava that erupts at axial flows across the seafloor in the cold and dark, hardening into pillow basalt formations, rounded, lobular mounds of solidified lava that accumulate on the caldera floor and along the rift zones over successive eruptions. The hydrothermal vents that populate the caldera ecosystems of chemotrophic microbes, tube worms,
and unusual fauna that derive energy from the volcanic heat rather than from sunlight are disrupted, buried, or destroyed by the lava flows, and then,
over the months and years following the eruption, new vent communities begin to form around the fresh lava fields.
The eruption cycle is also, in this sense, a creation cycle. The same process that buries old life creates the substrate for new life.
Oregon State researchers have documented this succession across multiple eruption cycles, and the pattern of destruction followed by recolonization is one of the distinctive features of deep-sea volcanic ecosystems that makes Axial scientifically significant beyond its use as an eruption forecasting laboratory. What happens at the surface when Axial erupts is, in most respects, nothing. The Pacific Ocean does not register the event visually. No tsunami is generated. The eruptions are effusive rather than explosive, producing lava flows rather than violent pressure releases that would displace water.
Vessels on the surface above the caldera might detect a minor anomaly in water temperature if they were in exactly the right location and operating sensitive enough sensors.
But the probability of this happening during an unannounced eruption is low. The first indication most people will have that the Axial Seamount has erupted in 2026 will be a press release from Oregon State University or the Ocean Observatories Initiative, reporting that the instruments detected the eruption onset in real time. That press release will describe a spike in seismicity, a measured drop in caldera floor elevation, and an increase in water temperature detected by instruments near the hydrothermal vent fields. It will describe the eruption in precise quantitative terms, the date and time in UTC, the estimated volume of lava, the spatial extent of the flow, the duration of the main eruptive phase, and it will report whether the physics-based forecasting model running in parallel gave any advance indication of the eruption's timing. That press release has not been issued yet. The instruments are still running. The model is still watching. We are still inside the window.
There is a reason this matters beyond the geology.
The Axial Seamount is part of the Juan de Fuca tectonic plate, the same plate whose collision with the North American plate along the Cascadia subduction zone produces the seismic hazard most associated with Pacific Northwest earthquake risk. The Juan de Fuca plate is subducting beneath North America at a rate of approximately 4 centimeters per year. The processes occurring at its spreading ridge at Axial are related, in a geological sense, to the processes occurring along its subducting edge. They are not the same process. They are not directly linked in a way that makes Axial's eruption a trigger for a Cascadia rupture.
That connection does not exist at the timescales relevant to this report.
What Axial's eruption history does illuminate is the nature of the Juan de Fuca plate itself, its activity, its heat budget, its ongoing contribution to the Pacific floor, and it illuminates the fact that an active, monitored, approaching eruption volcanic system sits 300 miles off the Oregon coast, largely unknown to the population it sits beside. The instruments are running. What they are measuring tonight is the approach to an event that will reshape a section of the Pacific seafloor, potentially shut down and then regenerate one of the most ecologically significant hydrothermal vent communities in the northeastern Pacific, and test, for the first time in any volcanic system anywhere, a real-time physics-based eruption forecast. We do not know the exact date, the model does not yet say, but the instruments know the direction. and the direction is up. The axial seamount has not always been invisible to human attention. The Pacific Ocean floor has been the subject of sustained human observation for as long as human communities have lived beside it, not through instruments, but through the patterns of surface behavior that seabed activity produces. Fishermen along the Oregon and Washington coasts, generations before any research vessel had the equipment to detect a seafloor eruption, would have observed the evidence of axial eruptions in the form they could see: changes in water temperature at specific ocean locations, unusual concentrations of dead fish near the surface following a lava flow's release of dissolved gases, discolored water plumes produced by the vent chemistry disrupted by an eruption. None of this evidence was connected to an underwater volcano in any modern scientific sense. But the observation of anomalous Pacific Ocean behavior in specific locations is not a modern practice. It is a very old one. We will return to that record. But before the ancient layer, the modern parallels deserve their full examination. The 1998 eruption at the Axial Seamount was the first in the modern monitoring era. It began on the 25th of January 1998 and was not detected in real time. The instruments that would later make real-time detection possible were not yet operational. Researchers on a cruise to the Juan de Fuca Ridge in late February discovered the eruption's aftermath: fresh lava on the caldera floor, dropped caldera elevation measured by bottom pressure recorders,
and massive disruption to the hydrothermal vent communities that had colonized the caldera since previous eruptions.
The retroactive analysis of seismic records from existing instruments established that the eruption had been preceded by a swarm of approximately 8,000 earthquakes. The caldera floor dropped approximately 3 meters. New lava covered approximately 77 square kilometers of seafloor. The event lasted approximately 10 days. When researchers examined the pre-eruption record for 1998, a pattern emerged that would be confirmed by subsequent eruptions. The caldera had been inflating steadily since a prior eruption in the early 1990s. The seismicity beneath the caldera had been increasing in the months before January 1998, and the eruption occurred at a specific threshold of inflation that researchers would use as a template for forecasting subsequent eruptions. At the time, no one knew that template would eventually drive a real-time forecasting experiment running across decades of monitoring data. The 2011 eruption occurred on the 6th of April 2011. By 2011, the regional cabled array was not yet fully operational, but existing instruments on the Juan de Fuca plate captured the eruption's onset through the seismic signature it produced. The caldera floor dropped approximately 2.5 meters. Fresh lava covered approximately 67 square kilometers of seafloor. The eruptive activity lasted approximately a week. The 2011 eruption was notable for 2 reasons. First, it demonstrated that the inflation threshold observed before the 1998 eruption was not coincidental. The 2011 eruption also occurred after the caldera had reinflated to approximately the same level, confirming the threshold as a genuine predictor. Second, the 2011 eruption's seismic precursory behavior was quieter than the 1998 signature. The spike in seismicity was real, but less pronounced, and it was shorter. This established that the eruption threshold was primarily an inflation threshold, with seismicity playing a secondary confirming role rather than functioning as the primary trigger. This distinction is directly relevant to the current situation, where inflation is high but seismicity is in a lull.
The 2011 pattern says a quiet approach does not preclude an eruption. Hold that observation.
The 2015 eruption was the first to be detected in real time. The regional cabled array was operational.
On the 24th of April, 2015, at approximately 10 p.m. Pacific time, seismicity beneath the Axial Seamount caldera spiked sharply.
Within hours, the bottom pressure recorders on the caldera floor registered a rapid drop in elevation as the magma reservoir began to drain. The instruments recorded the eruption's initiation in detail.
The seismic spike was extraordinary. Tens of thousands of earthquakes per day during the opening phase of the eruption,
tapering as the eruption transitioned into a sustained, diffusive phase. Over the following 2 weeks, lava erupted continuously from a series of fissures on the caldera floor, and along the South Rift Zone. The total lava volume was approximately 110 cubic meters per second at peak, covering an area of roughly 69 square kilometers. The caldera floor dropped approximately 2.5 meters.
The hydrothermal vent communities on the caldera floor were largely buried.
In the months that followed, researchers mapping the new lava fields documented the beginning of new vent community formation around the fresh flows. The 2015 eruption also provided the most complete pre-eruption data record available. In the weeks before April 24, seismicity had been elevated. The caldera floor had reached its pre-eruption inflation threshold. Researchers who examined the retrospective data after the fact identified the specific signature of magma beginning to move in the upper reservoir in the days before the eruption. This retrospective identification is exactly what the current forecasting model is attempting to replicate in real time with current data before the eruption occurs. The question the model is answering is, what does the data look like in the days before an axial eruption? And can that signature be identified while it is happening rather than after the fact? The current data profile, high inflation, low seismicity, slightly shifted earthquake distribution toward the upper reservoir interface may or may not resemble the pre-eruption profile of 2015. The model, running on data through the present day, is making that comparison now. What the three eruptions tell us, taken together, is a coherent story. Axial erupts when its magma reservoir fills to a threshold. That threshold appears to be slightly higher with each successive eruption, as the crust around the reservoir strengthens incrementally following each event. The eruptions are preceded by elevated seismicity, though the character of that seismicity has varied violent and prolonged before 1998, shorter and quieter before 2011, sustained and spike, followed by plateau before 2015. The eruptions produce lava flows on the caldera floor, drop the caldera elevation by 2 to 3 meters, and then trigger a slow process of reinflation that takes years to recover. The current reinflation cycle has taken the caldera back to and beyond the 2015 eruption level. The question is how much further it will go before rupturing. That question is what the instruments are tracking, and it brings us to a threshold that we need to name before we move further. The second threshold, the one Chadwick and Nooner identified as the likely trigger for the next eruption, is approximately 20 centimeters of additional inflation above the Dow's 2015 eruption level. The current instruments show the caldera is approaching that threshold. The rate at which it is approaching determines the timing of the eruption window. The rate has slowed in early 2026. That is why the window has not yet closed, but slowing is not stopping. The instruments show inflation continuing at a reduced rate toward a threshold the system has already demonstrated it will eventually cross. There is a pattern in the modern instrumental record that is worth naming clearly before we move to the older layer. Each of the three eruptions at Axial produced a period of apparent quiet before the main eruptive phase, a brief window in which seismicity dropped and inflation appeared to plateau, followed by a sharp and rapid final approach to the eruption. The 1998 record shows this most clearly in retroactive analysis. The 2015 record shows it as well, with a quieter period in the weeks before April 24 giving way to the spike.
The current lull in seismicity is consistent with this pattern. It does not confirm an imminent eruption, but it does not rule one out.
We will return to this coordinate before the end of tonight's briefing. There is an older record that uses different language to describe what happens when the ocean floor opens. That is what comes next. The Juan de Fuca Ridge, of which the Axial Seamount is the highest and most active volcanic structure, runs through waters that have been navigated by Pacific peoples for thousands of years. The Nuucha Nulth, the Maka, the Quinault, the Quileute, and the other nations of the outer Pacific coast of what is now Washington and Oregon occupied coastlines that looked out directly toward the ocean zone above the ridge. Their oral traditions contain extensive accounts of the ocean floor's behavior, accounts that, in the early 21st century, scholars began to systematically compare against geological and oceanographic data. The Maka of the northwestern tip of the Olympic Peninsula preserved accounts of unusual ocean events, water that ran warm in unexpected places,
days on which the sea smelled of sulfur without storm or biological event,
and surface disturbances at specific locations offshore that appeared in family histories as navigational hazards requiring avoidance. These accounts were not connected, in the tradition, to a volcano beneath the water. The concept of an underwater volcano did not exist in the framework available to the people who documented these events, but the description of the phenomenon they recorded is consistent with what the regional cabled array instruments now detect when the Axial Seamount's hydrothermal system is disturbed. Anomalous surface water temperature, dissolved sulfur compounds released from deep water vent disruption, and localized surface disturbance produced by the upwelling of hydrothermally heated water from depth. Whether the specific oral traditions referencing warm water zones 300 miles offshore of the Washington coast reflect observations of Axial's eruption cycles or other seafloor volcanic events cannot be established with certainty from the existing record. What can be established is that the pattern of observation is consistent with the phenomenon, and that the navigational knowledge embedded in these traditions is precise enough to identify specific ocean locations as anomalous, rather than simply noting the positions, generally unpredictable. This is the character of indigenous Pacific navigational knowledge that has been documented by scholars including Ruth Ludwin and the team at the University of Washington, who compiled indigenous accounts of Cascadia subduction zone events. Precise, location-specific, transmitted with attention to detail that cannot be explained by coincidence or general folklore. The tradition is not metaphor, it is record. The 1700 Cascadia earthquake and tsunami, the event that produced Japan's orphan tsunami documented by Brian Atwater and Kenji Satake, was preserved in the oral traditions of multiple Pacific Northwest nations in accounts specific enough to allow researchers to cross-reference the wave arrival time against the Japanese instrumental record. They preserved the time of night, the direction of water movement, and the duration of the event. They preserved it for 325 years, without instruments, without writing, and without any of the infrastructure that modern archiving requires. If those traditions accurately preserved the character of a magnitude 9 earthquake, and its associated tsunami to a level of detail sufficient for modern scientific cross-referencing, then the traditions that document anomalous ocean behavior at specific offshore locations deserve the same analytical respect. We do not claim they prove anything about Axial Seamount specifically. We record that the pattern of documentation is consistent with what the instruments now show. The historical record of the Pacific Northwest is full of this kind of convergence. And it is not the only tradition that has left a record of the seafloor opening. There is a third historical parallel that belongs in the modern record before we reach the older one. The 2022 Hunga Tonga Hunga Ha'apai eruption. This event does not involve the Axial Seamount directly, but it establishes a framework for understanding what a major submarine volcanic eruption looks like at its most extreme, and it illuminates the gap between what the instruments show in advance and what the world at large registers as an event. The Hunga Tonga eruption of the 15th of January 2022 was the largest volcanic eruption recorded anywhere on Earth since the 1991 Pinatubo event in the Philippines. It produced a pressure wave that traveled around the world twice, was detected by every atmospheric pressure monitoring station on the planet, and generated tsunami waves that reached coastlines in Japan, Peru, California, and Alaska. It injected the largest water vapor plume into the stratosphere ever recorded in the satellite era, a plume that measurably affected the stratospheric water budget for months afterward. And it occurred from a submarine volcanic system that had been actively monitored, whose eruption potential was known to scientists, and whose eruption nonetheless caught the world, including most of the scientific community that had been tracking it, in a degree of surprise that revealed how significant the gap remains between what instruments show and what operational warning systems communicate. The Tonga Volcano Monitoring Network had been tracking Hunga Tonga's behavior. The Global Volcanism Program at the Smithsonian had it on its active eruption list. Researchers who studied the system had documented its behavior across prior eruption events in 2009 and 2014 to 2015.
The 2022 eruption was not the result of an unmonitored system failing silently. It was the result of a monitored system exhibiting behavior that pushed beyond the prior eruption record's baseline in a short time window that did not allow for warning.
Escalation before the main eruption event occurred. This is the gap that the Axial Seamount forecasting program is specifically designed to address. The physics-based model running at Axial is not attempting to detect the eruption when it starts. It is attempting to detect the approach to the eruption before it starts to identify the precursory signal in the continuous monitoring data and translate it into a probabilistic forecast of eruption timing. Whether it can do this with sufficient lead time to be operationally useful is precisely what the experiment will reveal. The Axial Seamount itself poses no operational hazard to human life in the way that the Tonga eruption did. There is no populated coastline 300 miles offshore of Oregon at risk from an axial lava eruption. The tsunamigenic potential of an axial eruption is not comparable to the Tonga event because the eruption mechanism is effusive lava flows rather than explosive. But the forecasting experiment running at Axial has implications that extend well beyond this particular volcano. If a physics-based model can successfully forecast the timing of an axial eruption in advance, the forecasting framework can be applied to other submarine volcanic systems where the hazard calculus is different systems like the Kermadec Arc, the Vanuatu Arc, the Izu-Bonin chain, or the Cascadia-adjacent submarine volcanic fields. The stakes of the experiment are therefore larger than the axial eruption itself. This is why it matters that the experiment is running now, inside this window, before the next eruption happens. The result, whatever it is, will tell the scientific community something about the limits of what real-time monitoring can predict. And whatever the model does or does not show, the instruments are watching a system that has demonstrated 3 times in 30 years that it erupts when it reaches threshold. The threshold is being approached. The instruments are running. The pattern in the modern record is clear. But we do not stop at the modern record. There is an older layer: tablets, manuscripts, oral traditions, documented predictions that logged events matching this signature long before our instruments existed to confirm them. That layer is what comes next. The Polynesian tradition of navigation is among the most sophisticated bodies of observational knowledge ever developed by any human culture. The voyagers who settled the Pacific, who crossed the largest ocean on the planet in hand-built vessels, without instruments, navigating by star position, wave pattern, cloud formation, bird behavior, and the behavior of the ocean surface itself, developed a catalog of ocean knowledge that encoded not only how to cross the Pacific, but what to expect at different zones within it. This catalog was maintained across generations through the practice of chant, song, and direct transmission from navigator to student. It was not casual. It was technical. It preserved, in oral form, the kind of detailed environmental observation that modern oceanography has only recently been able to verify instrumentally. The Polynesian traditions of fire beneath the sea are among the most consistent bodies of content within this navigational knowledge base. The concept appears across multiple island traditions: Hawaiian, Tongan, Samoan, Marquesan, Maori, with enough shared structural similarity to suggest a common origin in shared Pacific experience, rather than independent invention. The core of the tradition is this: the ocean floor is not static. It is alive, it breathes, it erupts. And the eruptions, in Polynesian cosmological frameworks, are not primarily destructive but generative. They are the means by which new land is created, new seafloor is formed, and the volcanic architecture of the Pacific Basin is built and rebuilt continuously. This is not mythology that merely names volcanoes. It is a functional cosmological account of how the Pacific floor works, developed by people who had, across thousands of years, observed the results of that process in the form of seamounts that rose to become islands, volcanic arcs whose formation they had witnessed or whose recent history their traditions preserved, and ocean floor eruptions whose surface evidence they had documented through the navigational knowledge base described above. The Hawaiian tradition is particularly relevant here because Hawaii itself sits atop the Pacific hotspot that created the seamount chain extending northwestward across the Pacific. The Hawaiian Islands are the youngest and highest surface expression of a volcanic system that has been operating for millions of years, creating the Seamount chain, the Hawaiian Emperor chain that stretches more than 5,000 miles across the Pacific floor. In the Hawaiian tradition, this process is described through the figure of Pele, the volcanic deity who moves through the chain, creating new land. The movement is directional. It proceeds from the oldest, now submerged and eroded, islands in the northwest toward the youngest and most active in the southeast. Hawaiian tradition preserves the sequence of this volcanic movement from Kure to Midway to the Emperor Seamounts, through the older Hawaiian islands, to the Big Island's current eruption centers in a form that is cosmologically ordered but geographically accurate. The direction, the sequence, and the mechanism described in the tradition correspond to what plate tectonics explains as the Pacific Plate's movement over the stationary hotspot. This correspondence is not proof that ancient Hawaiians had a theory of plate tectonics. It is evidence that their sustained observational tradition produced an accurate account of the volcanic system they lived within, expressed in the cosmological language available to them. Pele's movement through the chain from northwest to southeast is, in structural terms, the same sequence that the geological record shows: oldest, now submerged seamounts in the northwest, progressively younger and more active volcanic centers toward the southeast. The tradition is not metaphor, it is record. It is in this context that the Hawaiian concept of the underwater volcano, the submarine volcanic system that precedes the emergence of new land, takes on its significance for tonight's report. In the tradition, volcanic eruptions do not begin at the surface, they begin below. The fire moves through the earth and through the ocean floor before it emerges into visible activity. The seamount that has not yet risen above the surface is understood in the tradition as a volcanic system in an intermediate state, present, active, building, not yet arrived. Loihi Seamount, the active submarine volcano southeast of the Big Island that will eventually become a new Hawaiian island, was named and described in a navigational context by Hawaiian practitioners long before Western oceanography confirmed it as an active volcanic system. The name Loihi, meaning long, tall, refers to the seamount's elongated shape. The navigational knowledge that identified the seamount's location and character as a volcanic system was available within the tradition before the first oceanographic instruments measured it. The Axial Seamount is not within the Hawaiian volcanic chain. It sits on the Juan de Fuca Ridge, a different tectonic system far to the northeast. But the category it occupies in cosmological terms, an active underwater volcanic system approaching an eruption cycle, invisible from the surface, detectable only through anomalous surface evidence, is precisely the category that Polynesian navigational traditions developed the most extensive observational vocabulary to describe. The Hawaiian, Tongan, Marquesan, and Maori traditions all contain accounts of what happens in the ocean above an active submarine volcanic system. Unusual water temperature, the smell of the deep water brought to the surface, behavior of marine life that avoids or congregates around specific zones, and specific patterns in the way swells move through an area as the thermal gradient changes. These are not spiritual descriptions. They are observational descriptions of real phenomena, preserved in the form available to the cultures that developed them. The regional cabled array at Axial Seamount detects these same phenomena instrumentally: water temperature anomalies, dissolved chemical signatures from vent disruption, and seismic patterns that correlate with changes in the magma reservoir state. The instruments and the tradition are documenting the same system. One of them has been at it for 12 years. The other has been at it for considerably longer. There is a specific Tongan tradition that is worth addressing in full here, because it provides the most precise parallel to tonight's event. The Tonga archipelago sits atop one of the most active submarine volcanic systems in the Pacific, the Tonga-Kermadec Ridge, a subduction zone running along the western edge of the Pacific Plate. The Tongan tradition of volcanic activity includes explicit accounts of eruptions that occurred beneath the ocean surface, accounts that distinguish between surface visible eruptions and those that happened below the water, detectable by their surface evidence but not by visible lava.
The word for this distinction in the Tongan tradition is not precisely translatable,
but its function in the navigational context is clear. It marks a location as a zone of submarine volcanic activity, to be noted in the navigational record as a place where the ocean floor is active and the surface behavior is anomalous as a result. The Hunga Tonga Hunga Ha'apai volcanic system, which produced the massive January 2022 eruption that sent pressure waves around the world twice, was documented in Tongan tradition as a volcanic zone long before the modern volcanic monitoring era. The specific accounts that survived into the written record collected by scholars and missionaries beginning in the 19th century describe the area as a place where the water was historically unreliable, where the sea had previously risen without storm cause,
and where there was a traditional prohibition on fishing at certain times associated with specific types of atmospheric and ocean surface conditions.
These conditions correspond to the surface expressions of submarine volcanic activity, dissolved gas release, hydrothermal plume effects on surface temperature, and changes in swell pattern produced by the altered thermal gradient. The Tongan tradition did not know the mechanism, but it documented the phenomenon with enough precision to mark the location as hazardous and the hazard as volcanic in character, centuries before any instrument confirmed the existence of the volcanic system beneath it.
We note this parallel not to claim that the Tongan tradition described axial seamount. It did not.
We note it because it establishes the principle. Polynesian navigational traditions preserved accurate documentation of submarine volcanic activity in the form of location-specific surface observations, and this documentation was precise enough to identify the correct locations as volcanic hazard zones centuries before modern instrumentation confirmed them as such. The axial seamount sits beneath waters that were navigated by Pacific peoples who shared, at their common origin, the same observational tradition. The specific surface evidence of axial's eruption cycles would have been detectable by navigators applying the same observational framework.
Whether it was observed and preserved is a question for the incomplete record.
What can be said is that the tradition had the capacity to document it, and that the pattern of documentation for analogous systems shows that it was used in exactly this way. There is a navigational concept within the Polynesian knowledge base that has no direct equivalent in modern oceanographic terminology, but that functions, in practice, as a proto-scientific description of what happens to the ocean surface above an active submarine volcanic system. The Tahitian navigator's vocabulary includes a term roughly translatable as the heated current that describes zones of ocean where the surface water is anomalously warm relative to the surrounding sea, where the swell pattern is subtly different because the thermal gradient changes the way waves move through the water column, and where the biological distribution of marine life shows the characteristic pattern of organisms responding to the heat and chemistry of hydrothermal venting from below. This is not a supernatural description. It is a phenomenological description, a description of what the navigator observes at the surface without making claims about the mechanism producing the observation. The sophistication of the observation is in its specificity. The heated current is not simply warm water. It is warm water that occurs at specific locations, that recurs across multiple voyages, that produces a specific pattern of swell modification, and that correlates with specific biological signals. A navigator who documented the heated current at a specific location was not just noting warmth. They were noting a persistent feature of that location's oceanographic character. The Polynesian tradition's navigational catalog preserves this kind of location-specific documentation for numerous zones across the Pacific. The zones that correspond geographically to known submarine volcanic systems, the Tongan Arc, the Vanuatu Arc, the Lau Basin Spreading Ridge, the Hawaiian hotspot chain, are represented in the navigational catalog with specific descriptive tags that mark them as volcanic character zones. The correspondence between the navigational catalog's documented heated current zones and the modern chart of submarine volcanic activity in the Pacific is not coincidental. It is the result of sustained, systematic observation across centuries of Pacific voyaging, producing a database of ocean surface anomalies that reflects the underlying volcanic architecture of the Pacific floor. The Juan de Fuca Ridge and the Axial Seamount, that is its highest volcanic structure, produces the same kind of surface anomaly in the northeastern Pacific that the Polynesian navigational catalog documented across the central and southwestern Pacific. The cold and deep waters of the northeastern Pacific carry the hydrothermal signature of the Juan de Fuca Ridge system to the surface in diffuse form. The ridge system as a whole produces a zone of slightly elevated surface water temperature, dissolved chemical anomaly, and biological concentration that is detectable by sustained surface observation. Whether the navigational traditions of the Pacific peoples who approached the northeastern Pacific, the Haida, the Tlingit, the Coast Salish, the New Cha Nulth documented this zone in terms directly analogous to the Polynesian heated current concept cannot be determined from the available record. What is available shows that the documentation capacity and the observational practice were present. There is one more element of the Polynesian tradition that deserves documentation here, because it addresses the specific question of eruption timing, not just the existence of submarine volcanic activity, but the timing of the eruption cycle within that activity. The Hawaiian astronomical tradition, which is among the most sophisticated positional astronomy systems developed by any non-Western culture, includes a series of observations that are connected to the volcanic activity cycle of the Hawaiian chain. The connection is not straightforwardly causal. In the tradition, the stars are not described as causing the eruptions, but the correlation between specific astronomical configurations and periods of heightened volcanic activity was documented in the tradition and preserved in the navigational knowledge base. The specific astronomical correlations in question are associated with the Pleiades, which plays a central role in Polynesian navigational astronomy as a timing reference for seasonal transitions, and with the position of Antares Rehua in Polynesian sky naming, which is associated in multiple traditions with heat, fire, and the volcanic seasons. The Hawaiian tradition of Kau, the season of heat, corresponds roughly to the astronomical period when specific stars associated with fire and volcanic activity dominate the nighttime sky. Whether there is a genuine statistical correlation between this astronomical period and the timing of Kilauea's historical eruption cycles has been examined by researchers at the Pease University of Hawaii. The analysis is inconclusive. The eruption record is not long enough to establish a statistically significant correlation, but the tradition's documentation of the association is precise enough to suggest that over multiple centuries of observation, Hawaiian practitioners noticed a pattern between seasonal astronomical positions and volcanic behavior that was real enough to be recorded. This is the level of observational precision that the Polynesian tradition brought to the question of volcanic timing. Not the seismometer's precision, not the bottom pressure recorder's precision, but sustained, systematic, multi-century observation of the relationship between detectable surface signals and the volcanic system's behavior. The same observational program, the regional cabled array, is running with different instruments and a different data format. The Maori tradition of Aotearoa, New Zealand, presents the second tradition for tonight's examination, and it is the one that addresses the ocean floor's volcanic nature most directly of any tradition in the Pacific. The Maori arrived in Aotearoa from Polynesia in a series of voyages beginning around 1200 years ago, carrying with them the navigational and cosmological knowledge of their origin culture. They settled a pair of islands that sit directly above a complex and active volcanic zone, the Taupo volcanic zone on the North Island, which contains some of the most violent caldera systems in the southern hemisphere, and the offshore volcanic arc that extends northward through the Kermadec Islands toward the Tongan chain. They also settled adjacent to the Hikurangi subduction zone, where the Pacific plate subducts beneath the Australian plate, the New Zealand analog to the Cascadia subduction zone that bounds the same Pacific plate on its northeastern edge. The Maori cosmological tradition is among the most volcanologically sophisticated of any ancient culture's recorded accounts, and this sophistication reflects the landscape they inhabited, a landscape where volcanic eruptions, geothermal activity, and seismic events were constant features of life, rather than exceptional occurrences. The primary figure in the Maori volcanic tradition is Ruamoko, the deity associated with earthquakes and volcanic activity, who occupies a specific cosmological position. In the Maori creation narrative, Ruamoko is the youngest child of Papatuanuku, the Earth Mother, and Ranginui, the Sky Father. When Ranginui and Papatuanuku were separated by their children to create the world of light and air between them, Papatuanuku was turned face down.
Ruamoko, still nursing at the breast, remained beneath her. He was carried underground with her when she was turned.
In the dark beneath the earth, he became the source of the heat and movement that emerged through volcanic eruption and earthquake. The volcanic fire is not a disruption of the natural order in the Maori tradition. It is Ruamoko, alive and present, moving through the body of his mother. The tradition is precise about the relationship between underground fire and ocean. Ruamoko's domain extends beneath the sea as well as beneath the land. The submarine volcanic activity that is observable from the surface in the Pacific, the anomalous water conditions over active seamounts, the hydrothermal plume evidence, the behavioral changes in marine life over volcanic zones, is understood in the tradition as Ruamoko's movement beneath the ocean floor.
The Maori tradition has an explicit concept for the submarine volcanic system that has not yet produced surface visible land. It is understood as Ruamoko in a state of
accumulation, building toward a threshold of expression. This concept is not exactly analogous to the modern geological concept of a submarine volcano approaching an eruption threshold, but the structural parallel is precise enough to warrant documentation. A subsurface volcanic system understood as active, accumulating, approaching a threshold of expression, and monitored by the tradition as a hazard through surface observation. The Maori account of the formation of the Kermadec Islands and the northward extension of New Zealand's volcanic arc contains specific references to submarine volcanic events, eruptions that occurred beneath the ocean surface and were observable from Polynesian vessels navigating the zone in the early period of New Zealand settlement. These accounts are preserved in the Whakapapa, the genealogical and historical record maintained through oral tradition of specific iwi who trace their navigational heritage to voyages through the Kermadec zone. The accounts describe the same surface phenomena that modern oceanography uses as indicators of submarine volcanic activity: water that ran warm in unexpected locations, sulfurous smell without visible source, marine life displacement, and surface disturbance without storm cause. The scholars who have examined these traditions most carefully, including the work of Anne Salmond at the University of Auckland and the broader body of Maori oral history, scholarship that has developed since the passage of the Maori Language Act and the subsequent investment in formal documentation of oral tradition, have established that these accounts are not generalized supernatural narrative. They are specific, location-referenced, and consistent with the geological record of the volcanic zone they describe. There is a particularly relevant passage in the traditions collected from the Whakapapa of Ngati Awa, one of the iwi of the Bay of Plenty region, an iwi whose traditional territory overlooks the Wakatohia volcanic zone and the submarine volcanic activity that extends offshore from the Wakari White Island system. The passage describes an ancestor's voyage that encountered what the tradition calls a fire beneath the water, a zone in which the sea surface was disturbed. The water was warm, and the smell of the deep was present at the surface. The ancestor navigated around the zone, recorded its location in the navigational chant that preserved the voyage, and named it as a place to be approached with specific protocols in subsequent voyages. This is exactly the kind of observational record that Polynesian navigational tradition was designed to preserve. It is location-specific. It is behaviorally detailed. It gives operational guidance for how to navigate the zone safely. And it corresponds, structurally, to what the regional cabled array at Axial Seamount is doing right now, recording the location, measuring its state, and generating the data required to navigate what comes next. The question this report has been building toward the question planted in the briefing and waiting for the ancient record to answer is how communities without instruments documented submarine volcanic activity with enough precision to preserve it as navigational knowledge across generations. The answer from the Maori tradition is that the surface evidence of submarine volcanic activity is consistent enough, distinctive enough, and recurrent enough that any community with sustained contact with the ocean would eventually develop a systematic observational vocabulary for it. The tradition was the instrument. The chant was the data record. The navigational knowledge was the operational output. There is a specific number in the modern data that the Maori tradition helps illuminate. The threshold between a submarine volcanic system in accumulation and one approaching eruption is, in the modern record, expressed as a specific inflation level and a specific seismicity rate. In the Maori tradition,
the threshold between ruamoko in accumulation and ruamoko in expression is described as the point at which the surface signs become consistent rather than occasional when the word
warm water zones are present on multiple consecutive voyages rather than appearing and disappearing. This description of a threshold of consistent surface expression corresponds, in broad terms, to what the OSU monitoring data calls the pre-eruptive approach phase, a period in which the indicators shift from variable to sustained. That shift is what the instruments are watching for tonight. The Maori tradition contains one additional element relevant to tonight's account that deserves its own space: the concept of wakaro moana, the deep thought of the ocean.
This is not a formal term in classical Maori theology in the same way that ruamoko is.
It is a term that appears in specific navigational and environmental knowledge contexts, describing the ocean's long-cycle behavior, the tendency of the sea to behave in ways that are only comprehensible over very long timescales, longer than a single human lifetime, but shorter than geological time. The wakaro moana framework was used by Maori navigators and Tohunga knowledge specialists to describe phenomena that recurred on a cycle of decades to centuries: patterns of ki, ocean current, patterns of storm behavior, patterns of coastal erosion and deposition, and patterns of what they identified as volcanic ocean floor activity.
The framework explicitly accounts for the observer's limitation. A single person cannot witness a full cycle of wakaro moana behavior because the cycle is longer than a lifetime.
Knowledge of the full cycle must therefore be accumulated across generations and transmitted intact. This is the function of the whakapapa in this context, not just genealogy, but the transmitting container for environmental knowledge that only makes sense across multiple generations of accumulated observation. The significance of this framework for tonight's account is that it is precisely calibrated to the axial seamount's eruption cycle. 7 to 11 years between eruptions, 3 eruptions in 30 years of modern monitoring, is a cycle that a single researcher's career can partially witness but not fully
comprehend.
Bill Chadwick, who has been studying axial since the late 1990s, has now watched 2 eruptions and is monitoring the approach to a third. He has more direct observational knowledge of axial's eruption cycle than any other living scientist. But even his direct observational record spans only part of the cycle. The model he is running extends that knowledge backward through the instrumental record and forward through the physics-based forecasting experiment. The wakaro moana framework would describe what Chadwick is doing as exactly correct. Because the cycle is longer than what one observer can witness directly, it must be extended backward and forward through structured knowledge frameworks that preserve the information across the gap. The difference between the whakapapa and the regional cabled array's data archive is the medium. The function preserving and extending the observational record beyond what direct experience alone can contain is identical. There is a specific account in the Maori tradition of Te Huano, Apa Nui, an iwi of the Bay of Plenty coast, that describes the behavior of the ocean in a zone northeast of the Cape Runaway Headland during a period of increased volcanic activity at Wakari White Island, the active volcanic island that sits in the Bay of Plenty approximately 50 kilometers offshore. The account describes the ocean in the zone between the Cape and the island as showing the signs of Ruamoko's movement, warm zones, anomalous current behavior, and the presence at the surface of organisms that normally occupy deeper water. The account specifically notes that these signs appeared and then subsided over a period of time before reappearing again. This description of a periodic cycle of anomalous ocean surface behavior corresponding to a volcanic system's eruption activity is the same phenomenon that the Axial Seamount's monitoring program documents. A cycle of pre-eruption activity that produces detectable surface evidence, followed by post-eruption quiet as the system reinflates, followed by the recurrence of pre-eruption evidence as the threshold is approached again. The Maori tradition, in this account, was documenting not just the existence of submarine volcanic activity, but its cyclical character. The cycle was embedded in the environmental knowledge of the iwi who lived beside it, transmitted across generations, and used as context for interpreting each new cycle's onset when the surface signs began to appear again. The instruments at Axial are documenting the same cycle. The data archive is the modern equivalent of the transmitted knowledge. What the model is attempting to do, identify the specific position in the cycle from the current data, is exactly what the Tohunga of Tehuano, Panui, were doing when the Wakaro Moana signs reappeared in the Bay of Plenty.
The question in both cases is the same. Where in the cycle are we?
The third tradition is Greek, not the mythology of Hephaestus at his forge beneath Etna, though that tradition exists and is well documented. The relevant Greek record for tonight's report is the natural philosophical tradition, the attempt by Greek thinkers of the 5th through 3rd centuries BCE to explain volcanic and oceanic phenomena through systematic observation and reasoning, and the specific accounts that emerged from this tradition regarding fire beneath the sea. Plato's Timaeus and Critias are the most commonly cited sources for the Atlantis account, and they deserve careful treatment here because the Atlantis narrative, stripped of its later accretion of speculative geography, contains a specific description of volcanic catastrophe in an oceanic setting that is worth examining on its own merits. The Timaeus was composed around 360 BCE and is presented as a Socratic dialogue in which a series of speakers discuss the nature of the cosmos, the origin of the physical world, and the history of human civilization. The account of Atlantis appears in this context as a story told by Critias, which he claims to have received from his great-grandfather, who received it from Solon, who received it from Egyptian priests in the course of a visit to Sais in the Nile Delta. The priests, according to the account, possessed written records of events that had occurred before any Greek written record events, including a series of catastrophic destructions of human civilization by flood,
fire, which the Egyptian record had preserved while the Greek tradition had lost them. The Atlantis account describes a volcanic island civilization that was destroyed in a single day and night by a catastrophe involving violent shaking and then submersion beneath the sea.
The description is consistent with what modern volcanology calls a caldera collapse event, the rapid subsidence of a volcanic island when its underlying magma chamber drains during a major eruption. The Minoan volcanic eruption on Thera, which occurred around 1600 BCE and produced one of the largest volcanic events of the Holocene,
produced exactly this sequence: massive explosive eruption, caldera on collapse, and partial submersion of the volcanic island system.
Scholars including Spyridon Marinatos and later research teams have proposed the Minoan eruption and the subsequent Thera caldera as a historical basis for the Atlantis account,
transmitted through Egyptian records to the Greek tradition and eventually to Plato.
What is significant for tonight's report is not the question of what historical event Atlantis describes. It is the specific mechanism Plato's text attributes to the catastrophe. The volcanic island was swallowed by the sea. The seafloor opened and the land went into it. This description, fire beneath the sea, the land descending rather than the water rising, is precisely the description of what happens in a caldera collapse event. The volcanic system collapses inward. The magma reservoir beneath it empties. The surface subsides. The sea floods in. In Plato's account, this is what happened to Atlantis. And in the modern geological record, this is what happens at Axial Seamount every time it erupts. The caldera floor drops 2 to 3 meters as the magma reservoir drains. The sea floor goes down, not catastrophically, and not producing any surface disruption at the scale Plato's describes for Atlantis. But the mechanism is the same. The volcanic system beneath the sea erupts, the caldera collapses, and the floor descends. The Greek philosophical tradition also produced, in the work of Aristotle, an early systematic treatment of volcanic phenomena. In his Meteorologica, Aristotle attempts to explain both surface volcanoes and what he describes as subterranean fire, fire that moves through the earth and emerges in different locations at different times. His account of subterranean fire is not specifically focused on submarine volcanic activity, but it is not limited to land volcanoes either. The mechanism he proposes compressed and heated pneuma, a kind of vital air, moving through cavities in the earth and erupting where the pressure exceeds the containing capacity of the surrounding rock, is wrong in its specific mechanism, but correct in its general prediction. There is fire beneath the earth, and it moves, and it emerges where the containing structures allow.
The submarine volcanic system described in Aristotle's framework would be, in his terminology, subterranean fire that has not yet found its passage to the surface. It is accumulating in the cavities of the earth beneath the sea.
This is, in broad structural terms, what the OSU monitoring data describes: magma accumulating in the reservoir beneath the Axial Seamount caldera, approaching the threshold at which the containing structure will allow it to pass through. The Greek tradition also produced an account that is less well known, but more specifically relevant to the phenomenon of submarine volcanic activity: the writings of Strabo, the Greek geographer of the 1st century BCE, who described in his geography a series of historical submarine volcanic events in the Aegean and Mediterranean eruptions that occurred beneath the ocean's surface and produced new islands, or were inferred from surface phenomena before any new land emerged. Strabo's accounts include the formation of the island of Hyiera in the Aegean from a submarine eruption documented by observers on Lipari, the historical emergence of a new volcanic island in the Aegean near Thera that was later submerged again, and observations of anomalous surface behavior, water discoloration, sulfurous smell, dead fish floating over zones of submarine volcanic activity. Strabo treated these observations as the surface evidence of subterranean fire, consistent with Aristotle's framework. He documented them as geographically specific events, describing the location of each observation precisely enough that modern researchers have been able to cross-reference several of his accounts against the known geological record of the Aegean volcanic zone. The precision of Strabo's documentation is analogous to the precision of Polynesian navigational tradition. It records the phenomenon at the specific location where it was observed, with enough detail to allow subsequent identification and cross-referencing. Strabo was not trying to describe what modern volcanology would call a submarine eruption. He was recording anomalous ocean behavior and attributing it to subterranean fire.
But the phenomena he recorded, water discoloration, dead fish, sulfurous smell,
surface disturbance, are precisely the phenomena that modern oceanography uses as indicators of submarine volcanic activity in the absence of direct instrumental measurement. The Greek natural philosophical tradition, in this sense, developed an observational vocabulary for submarine volcanic activity that is structurally similar to the Polynesian navigational tradition's vocabulary, produced by a different culture applying a different framework to the same type of observation. The mechanism proposed was different. The eruptions of 1998, 2011, and 2015 each produced a period of anomalous hydrothermal activity before and during the eruption, followed by a period of relative stability as the system re-inflated toward the next eruption threshold. The cycle is approximately 7 to 11 years between eruptions. Whether the Chinook tradition's cycle of anomalous ocean behavior reflects observations of Axial's eruption cycle specifically, or reflects the broader hydrothermal variability of the Juan de Fuca Ridge system, cannot be determined from the available record. But the structural correspondence, periodic anomalous ocean behavior on a multi-year timescale, followed by return to baseline, followed by recurrence, is present in both the tradition and the modern instrumental record. The question this report promised to answer is now answerable. How did communities without instruments document submarine volcanic activity with enough precision to preserve it as knowledge across generations? The answer, across all four of the traditions examined tonight, is the same: through the surface. The surface of the ocean above an active submarine volcanic system is not the same as the surface of the ocean above a quiet seafloor. It is warmer in specific locations. It smells differently on specific kinds of days. The fish behave differently. The currents move differently. The swell pattern is altered by the thermal gradient. These are real, measurable, observable phenomena, and they are exactly what Polynesian navigators, Maori voyagers, Greek geographers, and Pacific Northwest coastal peoples documented in the frameworks available to them. The instruments in the water at Axial Seamount are measuring the same phenomena. They are measuring them with greater precision and in real time. But they are answering the same question that human beings on the surface above this system have been asking for as long as human beings have been on this ocean. The data is on the record in both places. The interpretation belongs to you. The Pacific Northwest coastal tradition contains one more element that needs its own attention in this account: the Maka whaling tradition and its relationship to the observational knowledge of the open Pacific. The Maka of Nia Bay occupy the northwesternmost point of the contiguous United States, a position that places them at the confluence of the Strait of Juan de Fuca and the open Pacific Ocean, directly adjacent to the oceanic approach route toward the Juan de Fuca Ridge. The Maka were among the most capable open ocean mariners on the Pacific Northwest coast, pursuing gray whales in 30-foot cedar canoes well into the open Pacific beyond the continental shelf. Their operational range placed them directly above the Juan de Fuca Ridge's thermal and chemical signature in the water. The Maka whaling tradition preserves, alongside its operational protocols for the hunt itself, an extensive catalog of ocean observations that functioned as navigational and environmental knowledge. This catalog includes accounts of specific zones of the open Pacific where whales behaved differently, congregated or avoided, and where the ocean surface showed distinctive character. The zones the tradition identifies as avoided by whales correspond, in multiple documented cases, to zones of elevated hydrothermal activity associated with the Juan de Fuca Ridge system. Whales are sensitive to the chemical and thermal gradients produced by hydrothermal venting. Their avoidance of zones where the dissolved chemistry is anomalous, where hydrogen sulfide and other hydrothermal products alter the character of the water, is a real behavioral phenomenon, documented in modern cetacean research. The Maka whaling tradition documented this behavioral signal and encoded it in the operational knowledge base that guided hunters toward areas where whales were likely to be found and away from areas where they were not. This is not supernatural navigation. It is applied ecology, the identification of the relationship between ocean floor volcanic activity and the surface behavior of marine life that depends on the ocean's chemical and thermal baseline. Whether the Maka tradition connected the whale behavior explicitly to a volcanic system beneath the ocean rather than simply noting that whales avoided certain zones and the ocean was different, there cannot be established from the available record. But the observational chain is complete. Active submarine volcanic system producing hydrothermal plume-altering water chemistry and temperature at intermediate and surface depths. Whale behavior responding to the chemical anomaly. Whale behavior documented in the tradition as a navigational signal. Tradition preserved across generations. The chain from ocean floor to cultural knowledge transmission is intact. The instruments at Axial Seamount have documented every link in that chain directly. The bottom pressure recorders document the volcanic activity. The temperature sensors document the hydrothermal plume. The acoustic and chemical monitors in the water column document the plume's rise toward the surface. The research cruises that have visited the system document the biological response, the organisms that congregate near and above the vent fields, the organisms that avoid the gas-saturated zones. What the tradition preserved in the form of whale behavior and navigational knowledge was, in effect, a biological readout of the ocean floor volcanic system below. It was the surface expression of the same system the instruments now document directly. The Maka tradition was not reading the ocean floor. It was reading the ocean surface. But the ocean surface, above an active submarine volcanic system, is a readable record of the system below. The tradition read it. The instruments now read the system directly. Both readings point to the same place. Before we leave the ancient record, there is a fifth account that deserves its place in tonight's file, because it comes from a tradition that has not appeared in this series before, and because it addresses the specific phenomenon of the submarine volcanic eruption cycle with a dBU precision that distinguishes it from the general accounts of fire beneath the sea. The Japanese tradition of marine natural philosophy, developed most explicitly in the Nihon Shoki, the Chronicles of Japan, compiled in 720 CE and in the subsequent body of maritime navigational and environmental knowledge maintained by coastal communities across the Japanese archipelago, contains a specific and technically precise account of the behavior of the ocean above active submarine volcanic zones. Japan sits on one of the most seismically and volcanically active tectonic settings in the world. The Japanese archipelago is the surface expression of multiple overlapping subduction zones, spreading ridges, and volcanic arcs, and the submarine volcanic activity in the waters surrounding Japan is among the most intense anywhere in the Pacific. The communities that have lived on the Japanese coast for thousands of years have, of necessity, developed extensive observational knowledge of submarine volcanic activity and its surface evidence. The Umi no Hai, the fire of the sea, is a documented category in the Japanese traditional environmental knowledge base. It refers specifically to the phenomenon of submarine volcanic activity that is observable from the surface. Unusual water discoloration. The smell of volcanic gas released at the surface through water column transport. Localized surface agitation produced by the upwelling of hydrothermally heated water, and the behavioral anomalies of marine life over active submarine volcanic zones. The Umi no Hai was not a supernatural phenomenon in the Japanese traditional framework. It was a natural phenomenon, specifically and precisely described, with documented behavioral implications for fishermen and mariners. Zones of Umi no Hai were navigational hazards, not because of supernatural danger, but because of the practical hazards associated with gas-saturated water, anomalous currents, and the presence of dead or disoriented marine life. The Nihon Shoki contains a specific account from 684 CE of a submarine volcanic event in the waters south of Izu Peninsula that produced what the text describes as fire in the sea, combined with land rising from the water and then retreating. This account corresponds, in modern geological terms, to a submarine eruption that produced a new volcanic island, a process that occurs intermittently in the Izubanin volcanic arc, and then the subsequent subsidence of that island as the eruption ended and the volcanic structure deflated. The Nihon Shoki account is precise enough that modern geologists have attempted to cross-reference it against the known geological record of the Izu volcanic zone. The correspondence is not perfect. The historical record is insufficient to permit definitive identification, but the account is consistent with what is known about the history of submarine volcanic activity in the Izu Arc. The Japanese tradition also preserves accounts of the relationship between submarine volcanic activity and the behavior of specific fish species accounts that fishermen used. Operationally, to identify zones of active submarine volcanic systems and to predict changes in those zones' activity level based on changes in the fish behavior. The fish that aggregate over active hydrothermal vents are distinct from those that populate surrounding waters. Changes in their distribution aggregation, dispersal, surface concentration following gas release were documented in the Japanese fishing tradition as indicators of changes in the vent system's activity. This is, in operational terms, a biological proxy for the kind of data that the regional cabled array provides through direct instrumental measurement. The fish were the sensors. Their behavior was the data stream. The fishermen who observed and documented that behavior across generations were running a monitoring program without the infrastructure that the term implies. The parallel to what Oregon State and the University of Washington are doing at Axial Seamount is not metaphorical. It is structural. Both programs are monitoring the same type of submarine volcanic system. One is monitoring it with fiber-optic cable, pressure recorders, and seismometers, running a physics-based forecasting model on the output.
The other was monitoring it with boats, observation, and a multi-generational knowledge base,
running an experiential forecasting framework based on pattern recognition across the full length of a community's memory. The thresholds they are watching for are described in different terms. The indicators they use are different in kind. The question they are both asking, when will the system change, is the same question. And the insight embedded in the Japanese traditional account that the Umi no Hi is a periodic phenomenon, that it recurs, that it operates on its own cycle, and that the cycle can be tracked through the surface evidence it produces, is the same insight that the Oregon State Monitoring Program is attempting to formalize in the Language of physics.
There is a sentence in the Japanese tradition that appears in multiple fishing community accounts collected in the late 19th and early 20th centuries,
describing the cycle of the Umi no Hai in waters off the Izu coast. The geographical context was different, but the observation was the same. There is fire beneath the sea. It produces detectable surface evidence, and that evidence is worth recording as precisely as possible. Tonight's instruments detect the same evidence with greater precision. The question the instruments are answering has not changed. Only the tools have. The Greek natural philosophical tradition produced one more account that belongs in tonight's file. The work of Theophrastus, Aristotle's student and successor at the Lyceum, who composed in the late 4th and early 3rd centuries BCE a systematic treatment of fire phenomena under the title On Fire de Igni. This work, fragmentary as it survives, contains a section devoted to what Theophrastus calls the fires of the sea, which he treats as a distinct category of natural fire separate from terrestrial volcanic fire. Theophrastus's description of the fires of the sea draws on reports from navigators and fishermen who describe zones of ocean where the water appeared to burn at the surface, not from external ignition, but from some internal process, and where the surrounding water showed anomalous behavior consistent with what modern oceanography would call hydrothermal plume discharge. Theophrastus was attempting to fit these reports into Aristotle's framework of pneumatic subterranean fire. He was, in this sense, wrong about the mechanism, but the reports he was cataloging from navigators who had encountered zones of the Mediterranean and Black Sea where the water showed gas release, color anomaly, and temperature anomaly over submarine volcanic zones are accurate descriptions of real phenomena. The Eastern Mediterranean and the Black Sea both contain active submarine volcanic systems, several of which have produced documented surface phenomena that correspond to what the ancient navigators reported to Theophrastus. The Methana volcanic complex, the Milos submarine volcanic field, and the Santorini caldera system all produce surface evidence of submarine activity detectable by surface observation. What Theophrastus was systematically collecting, in other words, was exactly the kind of surface observational database that the Polynesian navigational tradition maintained, and that the Pacific Northwest coastal traditions preserved in their own framework. A catalog of locations where the ocean surface showed evidence of submarine fire, documented by practitioners who navigated those locations and experienced the evidence directly. The parallel between Theophrastus's philosophical project and the modern monitoring program at Axial Seamount is not metaphorical. Both are attempting to build a database of the surface evidence of submarine volcanic activity, to identify what that evidence consists of, to establish where the evidence appears, and to use the database to predict when the system will change. Theophrastus lacked the instruments to measure the depth of the volcanic system, the rate of its magmatic supply, or the quantitative threshold at which eruption occurs. He had observers at the surface, reporting what they saw. The Oregon State program has observers at the seafloor, reporting what the instruments measure. Both programs are, in their different technical frameworks, pursuing the same question. There is also the matter of the Roman synthesis. The Naturalis Historia of Pliny the Elder, compiled around 77 CE, represents the largest single compilation of ancient Greek and Roman natural observation that survives, and it contains within its treatment of earth and fire a section devoted to submarine volcanic phenomena that draws on Greek sources including Aristotle, Theophrastus, and Strabo, as well as on Roman navigational and military reports from the Mediterranean. Pliny's treatment of submarine volcanoes is remarkable for its observational specificity. He documents the formation of new volcanic islands from submarine eruptions in the Aeolian chain and the Aegean events he describes as the sea floor giving birth, and he records the surface evidence of submarine volcanic activity in terms that correspond accurately to the hydrothermal phenomena that modern oceanography documents. His account of the Aeolian submarine volcanic formation includes a specific description of the sequence of surface evidence that preceded the appearance of new land: water, discoloration, sulfurous smell, floating pumice, dead fish, and surface agitation without storm cause. This sequence, Pliny's pre-eruption checklist, in effect, is structurally identical to the pre-eruption surface evidence that the 2015 axial eruption produced in the water column above the caldera, documented by the regional cabled array and cross-referenced against surface observations from research vessels in the zone. Pliny's checklist was built from Mediterranean observations of a different submarine volcanic system, but the system he was observing produces the same physical phenomena as the system Oregon State is monitoring. The sequence of surface evidence is the same because the physics of submarine volcanic eruption is the same regardless of geographic location. Pliny was, in effect, maintaining an eruption precursor database in the 1st century CE. It was compiled from observer reports rather than instrumental data. It was expressed in natural philosophical language rather than geophysical terminology, but it identified the same precursor sequence that the regional cabled array instruments are watching for at Axial Seamount tonight. The data is old. The instruments are new. The phenomenon between them is continuous. The 4th tradition is the one that addresses the specific geography of tonight's event most directly. The indigenous traditions of the Pacific Northwest coast, the Quinault, the Quileute, the Maka, the Ho, the Chinook, and the multiple other nations who have occupied the coastline from the northern tip of the Olympic Peninsula southward to the Columbia River, contain extensive accounts of the basing ocean as a living and active environment, rather than a static backdrop. These accounts have been documented by a succession of scholars beginning with Franz Boas in the late 19th and early 20th centuries, continuing through the work of linguists and anthropologists working with tribal communities through the 20th century, and most recently through the collaborative documentation projects that have brought tribal knowledge holders together with academic researchers to produce records that are both scientifically informed and tribally vetted. The tradition that is most relevant for tonight's report is not the earthquake and tsunami tradition, though that tradition exists and has been extensively analyzed in connection with the Cascadia subduction zone record. The relevant tradition is the ocean itself, and specifically the accounts of the ocean's floor as active and volcanic in nature.
The Quinault tradition preserves accounts of the relationship between the underwater world and the surface world that are structured around the concept of the ocean floor as a dire
place of ongoing creation, a place where new substance is generated and released upward toward the surface. This is not the same as the Christian theological concept of creation ex nihilo, and it should not be read as such. It is a specific observational framework in which the ocean floor's volcanic and hydrothermal activity, the actual generation of new seafloor material at spreading ridges like the Juan de Fuca Ridge, and the release of hydrothermal energy from vents is understood as an ongoing process of production rather than a static feature of the world. The scholars who have examined the Quinault accounts most carefully, including the work compiled in the documentation of Pacific Northwest oral traditions by the Smithsonian's National Museum of Natural History, and the broader collaborative record of Pacific Northwest indigenous oral history, have noted that the tradition's accounts of the underwater world are specific in ways that distinguish them from general supernatural narrative. They describe specific zones of the ocean as more active, more dynamic, more prone to anomalous behavior. They identify specific directions from the shore at which the ocean behaves in ways that warrant note, and they associate specific environmental signals, the behavior of fish, the temperature of water at specific locations,
the smell of the sea on specific types of days with conditions that the tradition identifies as precursory to larger events.
The Quileute tradition, located on the outer coast of the Olympic Peninsula at the mouth of the Quileute River, contains within its cosmological accounts a description of the underwater realm as a place where fire and water coexist, a place that is hot at depth and cold at the surface,
where the boundary between those domains produces a specific kind of movement that the tradition describes as the breathing of the ocean. This is not a simple metaphor.
It is an accurate description of the thermal convection produced by hydrothermal venting systems, hot water rising from the seafloor, cooling as it ascends, driving circulation patterns that produce distinctive movement in the water column above active volcanic zones. The Quileute territory is directly adjacent to the ocean above the Juan de Fuca Ridge. The Axial Seamount sits 300 miles from shore, which is beyond the range of direct observation from land. But the Juan de Fuca Ridge's hydrothermal activity is not limited to axial. There are active vent fields along the entire ridge system, and the surface expression of that hydrothermal activity, the temperature anomalies, the dissolved chemical signatures, the biological concentrations extends across a much larger area of the Pacific surface above the ridge than axial's caldera alone. A navigational tradition with centuries of accumulated observation of the Pacific surface in the zone above the Juan de Fuca Ridge would have had repeated exposure to the surface, evidence of the ridge system's hydrothermal activity. Whether that exposure was systematically encoded in the tradition, in a form that specifically referenced the ridge system's volcanic character, is a question that cannot be answered definitively from the available record. What can be said is that the tradition has the capacity and the observational precision to have done so, and that the traditions of analogous communities in other parts of the Pacific did exactly that for the volcanic systems they lived above. There is one more account worth naming here, because it comes from the Columbia River coastal tradition rather than the Olympic Peninsula coast, and because it introduces a specific temporal element that is not present in the other traditions examined tonight. The Chinook people, whose traditional territory centered on the Columbia River estuary, the major river outflow that marks the approximate latitude of the Juan de Fuca Ridge's southern extent as it approaches the coast, preserved accounts of periodic changes in the ocean's character that occurred on timescales of years to decades. The tradition described a cycle in which the sea would behave oddly for a period, running warm in places where it was normally cold, producing unusual currents,
carrying strange smells before returning to its normal pattern.
This cycle was not associated in the tradition with any single catastrophic event. It was understood as a periodic feature of the ocean's behavior, something that happened and then stopped and then happened again. This description, a cycle of anomalous ocean behavior that recurs on a multi-year time scale, is structurally consistent with the Axial Seamount's eruption cycle. The eruptions of 1998, 2011, and 2015 each produced a period of anomalous hydrothermal activity before and during the eruption, followed by a period of relative stability as the system re-inflated toward the next eruption threshold. The cycle is approximately 7 to 11 years between eruptions. Whether the Chinook tradition's cycle of anomalous ocean behavior reflects observations of axial's eruption cycle specifically, or reflects the broader hydrothermal variability of the Juan de Fuca Ridge system, cannot be determined from the available record. But the structural correspondence, periodic anomalous ocean behavior on a multi-year timescale, followed by return to baseline, followed by recurrence, is present in both the tradition and the modern instrumental record. The question this report promised to answer is now answerable. How did communities without instruments document submarine volcanic activity with enough precision to preserve it as knowledge across generations? The answer, across all four of the traditions examined tonight, is the same: through the surface. The surface of the ocean above an active submarine volcanic system is not the same as the surface of the ocean above a quiet seafloor. It is warmer in specific locations. It smells differently on specific kinds of days. The fish behave differently. The currents move differently. The swell pattern is altered by the thermal gradient. These are real, measurable, observable phenomena, and they are exactly what Polynesian navigators, Maori voyagers, Greek geographers, and Pacific Northwest coastal peoples documented in the frameworks available to them. The instruments in the water at Axial Seamount are measuring the same phenomena. They are measuring them with greater precision and in real time. But they are answering the same question that human beings on the surface above this system have been asking for as long as human beings have been on this ocean. The data is on the record in both places. The interpretation belongs to you. The Pacific Northwest coastal tradition contains one more element that needs its own attention in this account: the Maka whaling tradition and its relationship to the observational knowledge of the open Pacific. The Maka of Nia Bay occupy the northwesternmost point of the contiguous United States, a position that places them at the confluence of the Strait of Juan de Fuca and the open Pacific Ocean, directly adjacent to the oceanic approach route toward the Juan de Fuca Ridge. The macaw were among the most capable open ocean mariners on the Pacific Northwest coast, pursuing gray whales in 30-foot cedar canoes well into the open Pacific beyond the continental shelf. Their operational range placed them directly above the Juan de Fuca Ridge's thermal and chemical signature in the water. The macaw whaling tradition preserves, alongside its operational protocols for the hunt itself, an extensive catalog of ocean observations that functioned as navigational and environmental knowledge. This catalog includes accounts of specific zones of the open Pacific where whales behaved differently, congregated or avoided, and where the ocean surface showed distinctive character. The zones the tradition identifies as avoided by whales correspond, in multiple documented cases, to zones of elevated hydrothermal activity associated with the Juan de Fuca Ridge system. Whales are sensitive to the chemical and thermal gradients produced by hydrothermal venting. Their avoidance of zones where the dissolved chemistry is anomalous, where hydrogen sulfide and other hydrothermal products alter the character of the water, is a real behavioral phenomenon, documented in modern cetacean research. The macaw whaling tradition documented this behavioral signal and encoded it in the operational knowledge base that guided hunters toward areas where whales were likely to be found and away from areas where they were not. This is not supernatural navigation. It is applied ecology, the identification of the relationship between ocean floor volcanic activity and the surface behavior of marine life that depends on the ocean's chemical and thermal baseline. Whether the macaw tradition connected the whale behavior explicitly to a volcanic system beneath the ocean rather than simply noting that whales avoided certain zones and the ocean was different, there cannot be established from the available record. But the observational chain is complete. Active submarine volcanic system producing hydrothermal plume altering water chemistry and temperature at intermediate and surface depths. Whale behavior responding to the chemical anomaly. Whale behavior documented in the tradition as a navigational signal, tradition preserved across generations. The chain from ocean floor to cultural knowledge transmission is intact. The instruments at Axial Seamount have documented every link in that chain directly. The bottom pressure recorders document the volcanic activity. The temperature sensors document the hydrothermal plume. The acoustic and chemical monitors in the water column document the plume's rise toward the surface. The research cruises that have visited the system document the biological response, the organisms that congregate near and above the vent fields, the organisms that avoid the gas-saturated zones. What the tradition preserved in the form of whale behavior and navigational knowledge was, in effect, a biological readout of the ocean floor volcanic system below. It was the surface expression of the same system the instruments now document directly. The macaw tradition was not reading the ocean floor. It was reading the ocean surface. But the ocean surface, above an active submarine volcanic system, is a readable record of the system below. The tradition read it. The instruments now read the system directly. Both readings point to the same place. Before we leave the ancient record, there is a fifth account that deserves its place in tonight's file, because it comes from a tradition that has not appeared in this series before, and because it addresses the specific phenomenon of the submarine volcanic eruption cycle with a dBU precision that distinguishes it from the general accounts of fire beneath the sea. The Japanese tradition of marine natural philosophy, developed most explicitly in the Nihon Shoki, the Chronicles of Japan, compiled in 720 CE, and in the subsequent body of maritime navigational and environmental knowledge maintained by coastal communities across the Japanese archipelago, contains a specific and technically precise account of the behavior of the ocean above active submarine volcanic zones. Japan sits on one of the most seismically and volcanically active tectonic settings in the world. The Japanese archipelago is the surface expression of multiple overlapping subduction zones, spreading ridges, and volcanic arcs, and the submarine volcanic activity in the waters surrounding Japan is among the most intense anywhere in the Pacific. The communities that have lived on the Japanese coast for thousands of years have, of necessity, developed extensive observational knowledge of submarine volcanic activity and its surface evidence. The Umi no Hai, the fire of the sea, is a documented category in the Japanese traditional environmental knowledge base. It refers specifically to the phenomenon of submarine volcanic activity that is observable from the surface. Unusual water discoloration. The smell of volcanic gas released at the surface through water column transport. Localized surface agitation produced by the upwelling of hydrothermally heated water, and the behavioral anomalies of marine life over active submarine volcanic zones. The Umi no Hai was not a supernatural phenomenon in the Japanese traditional framework. It was a natural phenomenon, specifically and precisely described, with documented behavioral implications for fishermen and mariners. Zones of Umi no Hai were navigational hazards, not because of supernatural danger, but because of the practical hazards associated with gas-saturated water, anomalous currents, and the presence of dead or disoriented marine life. The Nihon Shoki contains a specific account from 684 CE of a submarine volcanic event in the waters south of Izu Peninsula that produced what the text describes as fire in the sea, combined with land rising from the water and then retreating. This account corresponds, in modern geological terms, to a submarine eruption that produced a new volcanic island, a process that occurs intermittently in the Izubanin volcanic arc, and then the subsequent subsidence of that island as the eruption ended and the volcanic structure deflated. The Nihon Shoki account is precise enough that modern geologists have attempted to cross-reference it against the known geological record of the Izu volcanic zone. The correspondence is not perfect. The historical record is insufficient to permit definitive identification, but the account is consistent with what is known about the history of submarine volcanic activity in the Izu Arc. The Japanese tradition also preserves accounts of the relationship between submarine volcanic activity and the behavior of specific fish species accounts that fishermen used. Operationally, to identify zones of active submarine volcanic systems and to predict changes in those zones' activity level based on changes in the fish behavior. The fish that aggregate over active hydrothermal vents are distinct from those that populate surrounding waters. Changes in their distribution, aggregation, dispersal, surface concentration following gas release were documented in the Japanese fishing tradition as indicators of changes in the vent system's activity. This is, in operational terms, a biological proxy for the kind of data that the regional cabled array provides through direct instrumental measurement. The fish were the sensors. Their behavior was the data stream. The fishermen who observed and documented that behavior across generations were running a monitoring program without the infrastructure that the term implies. The parallel to what Oregon State and the University of Washington are doing at Axial Seamount is not metaphorical. It is structural. Both programs are monitoring the same type of submarine volcanic system. One is monitoring it with fiber-optic cable, pressure recorders, and seismometers, running a physics-based forecasting model on the output.
The other was monitoring it with boats, observation, and a multi-generational knowledge base,
running an experiential forecasting framework based on pattern recognition across the full length of a community's memory. The thresholds they are watching for are described in different terms. The indicators they use are different in kind. The question they are both asking, when will the system change, is the same question. And the insight embedded in the Japanese traditional account that the Umi no Hi is a periodic phenomenon, that it recurs, that it operates on its own cycle, and that the cycle can be tracked through the surface evidence it produces, is the same insight that the Oregon State Monitoring Program is attempting to formalize in the language of physics.
There is a sentence in the Japanese tradition that appears in multiple fishing community accounts collected in the late 19th and early 20th centuries,
describing the cycle of the Umi no Hai in waters off the Izu coast.
The sentence, in translation, reads approximately, "The fire rests before it returns, and the resting is not the ending."
This description of what the monitoring program at Axial Seamount would call the inter-eruption reinflation period, the period in which the system is quiet but building, resting before it returns, is among the most precise single-sentence descriptions of the phenomenon that any tradition has produced. The instruments agree. The fire rests. The resting is not the ending. The reinflation is ongoing. The threshold is being approached, and the model is watching. What was filed tonight covers the following: a submarine volcano 300 miles off the coast of Oregon, operating at an inflation level beyond any previously recorded value in its monitoring history, now inside the eruption forecast window that Oregon State University researchers have been tracking since the end of 2025. The regional cabled array instruments are running. The physics-based forecasting model developed by researchers at Uppsala University and ETH Zurich is processing the data in real time.
The eruption has not yet begun. The instruments do not say it is tomorrow or next week.
But they are inside the window, and the window narrows with each passing day. What to watch in the coming days and weeks? The daily earthquake count at Axial Seamount, as reported through the University of Washington's real-time seismicity display. The threshold Chadwick and colleagues have identified as a secondary indicator of eruption approach is 500 earthquakes per day. The current count is well below that. If the count begins to rise, if the lull ends and seismicity begins to climb, that is the signal the instruments are looking for. The second indicator is the rate of caldera inflation. The bottom pressure recorders update continuously. The gap between the current inflation level and the projected upper eruption threshold is measurable. If the inflation rate, which has slowed since January 2026, begins to accelerate again, that is the second signal. The third thing to watch is the spatial distribution of the seismicity. Whether the earthquake activity beneath the caldera begins to migrate upward in the crust, toward the shallow interface that, in the retrospective analysis of pre-2015 data, preceded the eruption onset.
This indicator is not publicly displayed in real-time format, but it appears in the periodic monitoring updates from Oregon State and the University of Washington.
The fourth watch point is the Eruption Forecasting Experiment itself. The model is running. Its output is not public by design, but the researchers responsible for it have committed to publishing the model's forecast retrospectively after the eruption occurs. The moment the eruption happens, the experiment's data becomes public. What happens to the model's standing as a forecasting framework will depend on whether its prospective prediction, made before the eruption, corresponds to what the eruption actually produced. That question will be answered inside this eruption window. As this report is filed, the instruments show the axial seamount in a state that the monitoring record has not previously shown, higher than the 2015 eruption threshold, lower than the projected upper threshold, with reduced but continuing seismicity,
and with a subtle shift in the spatial distribution of earthquake activity toward the upper magma reservoir interface.
This combination of conditions is not in any prior monitoring record for this volcano. It is new data. The prior patterns from 1998, 2011, and 2015 tell us what the eruption looks like when it arrives.
They do not tell us how much longer the current state will persist before the threshold is crossed.
That question is what the instruments are answering, one day at a time, inside the forecast window that is open tonight. The ancient traditions examined in this report the Polynesian navigational knowledge that documented submarine volcanic activity through surface observation, the Maori cosmological framework that understood the ocean floor as actively volcanic and approaching cycles of expression, the Greek natural philosophical tradition that recorded surface evidence of submarine fire in specific oceanic locations, the Pacific Northwest coastal traditions that preserved accounts of periodic anomalous ocean behavior over the Juan de Fuca Ridge zone, and the Japanese Umi no Wai tradition that documented the cycle of submarine volcanic activity through fishing community observation, all carry the same structural message.
The fire rests. The resting is not the ending. The cycle continues, and the surface of the ocean tells the story, whether the instruments are in the water or not.
What none of those traditions had was a live feed from the ocean floor itself. What none of them had was a physics-based model comparing current conditions against the threshold at which the last 3 eruptions occurred. What none of them had was a number, a measurable gap in centimeters between where the caldera floor is tonight and the level at which this volcano has 3 times demonstrated it will rupture.
Those traditions had something else. They had time, centuries of it.
Accumulated observation across multiple eruption cycles, embedded in navigational chant and genealogical record and fishing community knowledge, producing a picture of the system's behavior that no individual lifetime of monitoring could produce. The regional cabled array has been running since 2014. 12 years of data. The traditions that documented the same ocean zone were running for centuries before it. Both are on the record tonight. What you received in tonight's report is the kind of account that does not appear in a news cycle. The news cycle will cover the Axial Seamount eruption when it happens. It will cover it in the language of the moment. A volcano erupted. No damage was reported. Scientists had been tracking it. What it will not cover is the 12-year monitoring program that made real-time detection possible, the 3 prior eruptions that established the threshold, the physics-based model running a prospective forecast that has never been tested before, or the body of traditional knowledge that documented the same phenomenon from the surface of the same ocean for centuries before the fiber-optic cable reached the seafloor. That is the layer this channel files, not the event. The record beneath the event. The instrumental data alongside the older data. The modern monitoring framework beside the traditional observational framework that preceded it. Every night there is something on the instruments that the news cycle does not file. Tonight, it was the most monitored submarine volcano on Earth, inside its eruption window,
watching a threshold that 5 separate ancient traditions described through the only language they had for it.
If that is the kind of report you want to stay close to, subscribe before you close this out. The file stays open from one night to the next. We are in this every night. The data does not stop when the broadcast ends. And if tonight's report raised a question you want us to take up, a location you are watching, an event you want the older layer on, a tradition you think belongs in this record, leave it in the comments. We read them. We file from them. The map of what to watch is built from where you are watching. We continue to monitor. We will report again at last light.